Right. So let's resume our look at cylindrical polar coordinates. And if you recall, I mentioned that you start with the Cartesian coordinates x, y, and z, the origin here. And if you have an arbitrary point there with a radius vector r, make a projection of it onto the xy plane. This distance is rho. This angle is the azimuthal angle phi. This vertical distance is z, and the coordinates were r was given by rho, phi, and z in this fashion. What we need to look at are the unit vectors in this coordinate system at any point like this. One of them would of course be rho e rho itself. So that's the unit vector e subscript rho, and you bring it up there, it's in this direction, e sub rho. And remember that phi increases, so this thing goes in, that's e phi, so there's an e phi going into the board if this point is on the plane of the blackboard. And the third is of course the original Ez in this form. So the unit vector triad now depends on where you are, because E rho and E phi are phi dependent, and Ez of course is a constant vector. So now the relations that we had for Cartesian coordinates, the cross product of two members of the triad was equal to the third in cyclic permutation, reads like E rho cross E phi at any point. You take E rho, this vector, and drive a right-handed screwdriver, turn from E rho to E phi, which goes in there into the plane, and the screwdriver moves upwards. So this is equal to Ez, and similarly E phi cross Ez is equal to, so from phi you move to rho, the screwdriver moves out along E rho, and finally Ez cross E rho must be equal to E phi. And let's check this, drive a screwdriver from phi to rho, rotate, and it moves into the plane of the blackboard, which is E phi in this fashion. Okay. And what's the position vector of any point? R is equal to the sum of these two vectors. This vector plus this vector is equal to this vector here, the r vector, and therefore this is equal to rho times E rho plus z times Ez, this fashion. And you must remember that this is a function of phi. With this in term, when you write it in terms of Cartesian coordinates, there was a function of phi involved there. So this is what cylindrical polar coordinates look like, and they're useful in all problems where you have axial symmetry, where you have some kind of cylindrical symmetry about a specific axis, and it's very useful to call that the polar axis, this z axis, the vertical axis, and then use plane polar coordinates in a plane perpendicular to the z axis, to the polar axis. So it's useful in problems, this thing here, useful in cases of cylindrical or axial symmetry. If there's a preferred axis, then it's convenient to choose that as the z axis or a preferred direction and use plane polar coordinates in the plane perpendicular to it. So that's the use of cylindrical polar coordinates. We'll see, we'll come across problems where you use cylindrical polar coordinates very profitably, and these are the relations between the unit vectors here. One final point, the line element squared should also be written down. ds squared is d rho squared plus rho squared d phi squared plus dz whole squared. So cylindrical polar coordinates is a straightforward extension of plane polar coordinates, just adding the third Cartesian coordinate to it and nothing more than that. Okay. The ranges of these variables have been written down already. Rho is 0 to infinity, phi is 0 to 2 pi, and z is minus infinity to infinity. Okay. A little more intricate than that would be the case of spherical polar coordinates. here, and this is what these polar coordinates look like. So here's x, here's y, and here's z. That's the origin. If you took an arbitrary point here, and that was the radius vector to it, vector r, then spherical polar coordinates correspond to the following. You draw a projection onto the xy plane as before. That was rho, if you recall. So this quantity was equal to rho here. This distance is r from 0 to the point P. This angle here from the z-axis, from the vertical axis, positive vertical axis, moving down towards this point here, this radius vector here, this is called theta. And this angle here of this projection is phi as before. So if you like, you can imagine that a distance little r from the origin, draw a sphere of radius little r, then the spherical polar coordinates correspond to specifying the radius of this sphere, which is r. This angle theta, which is called the polar angle, as well as phi, which is the azimuthal angle as before. These are the spherical polar coordinates of an arbitrary point. It remains to say what these angles mean in geometrical terms. It's very simple. If you took the x-axis on the surface of this sphere, the point where this cuts the sphere, if you consider this to be 0 longitude, then it's clear that this phi is giving you angles of longitude. Constant phi would correspond to given meridian. On the other hand, theta, the angle from the polar axis, theta would be equal to pi over 2 in the xy plane. It would be equal to 0 on the positive z-axis, and on the negative z-axis it would be equal to pi. So theta is like the co-latitude measured from the north pole. Normal latitude is measured from the equator, and you talk about latitude north and latitude south, taking this to be 0 latitude on the equatorial plane. Here what we do is to start with the polar axis, the vertical axis, the positive z direction, to have angle theta equal to 0, and then from there you move down all the way to pi, which is down here in the negative axis. Okay. So the range of these variables is obvious. 0 less than equal to r less than infinity. The point could be either at the origin or anywhere in space, in which case it's got a finite length distance r. But theta runs from 0 up to pi, not 2 pi, but pi, because every point between 0 and pi over 2 has a positive theta between in the northern hemisphere, and every point between pi over 2 and pi, the theta is equal to, the point is in the southern hemisphere. Now it's interesting to ask what constant values of various coordinates is, and I'll come to that in a minute. Phi, as usual, has got this range here. Okay. Now it's convenient to picture these things in terms of what it means when one of these coordinates is constant. In the case of the plane, here's x and here's y. In the planar case, if I say x is constant, like 2, that's a line. X is 3 is here, y is 1 is here, y is 2 is out there, and so on. So these are lines parallel to one of the two axes, and they form a grid. In 3 dimensions, when I say z equal to 2, I mean a plane which is parallel to the xy plane at a height 2 above the xy plane. Okay? So these are x equal to constant, y, z equal to constant, are planes normal to whatever axis you keep constant. So if I say x is constant, it is a plane perpendicular parallel to the yz plane at whatever distance along the x-axis that this constant is. Okay. So in Cartesian coordinates this is completely trivial. On the other hand, when I go to polar coordinates, in plane polar coordinates, if I say phi is constant, it means I am along this line, a radial line starting from the origin going up to infinity. So phi is a different value here, phi is a different value here, and so on. So these are radial lines, or rather half lines starting from the origin going up to infinity. So phi equal to constant, some given value is a line, the locus of such points is a line. On the other hand, if I say rho is constant, then it's clear that the distance from the origin is constant, and what's happening is this is rho equal to some constant. Okay. These are concentric circles, and they cut the lines phi equal to constant at right angles, all of them. So these equi-coordinate surfaces, or in this case lines, are normal, just as in the earlier case a plane x equal to constant is normal to a plane y equal to constant, or a plane z equal to constant. Similarly, phi equal to constant is a half line that's normal to the curve rho equal to constant, perpendicular to it. That's why these are called orthogonal coordinates. In the case of cylindrical polar coordinates, z equal to constant is again planes, and rho and phi equal to constant is exactly as in plane polar coordinates, except in 3 dimensions. When I say that rho is equal to constant, z could be anything, and therefore I have the surface of a cylinder whose radial distance, whose radius is equal to whatever value of rho you specify. Similarly, phi equal to constant now would also be half planes rather than plane lines, because these things would come out in the z direction and be half planes. Okay. Now what about coordinates, spherical polar coordinates? Well, it's easy to see that r equal to constant is immediate, r equal to constant. This is a sphere of radius r about the origin, with the origin centered at the origin. So anytime I say r is constant in 3 dimensions, you are on the surface of a sphere of radius equal to that constant. Okay. What about phi equal to constant? Well, it's exactly as in the case of cylindrical polar coordinates. So if phi has this specific value, all points on this half plane at that value of phi are involved. So it's like a page, and this is the binding of the book. So it's the pages of a book, different angles correspond to different planes, correspond to pages, correspond to different values of phi as the book is opened out. Okay. What about theta equal to constant? Well, that's a little interesting, because now if this value of theta is constant, then no matter what phi is and no matter what r is, theta alone is constant. And since phi goes all the way around, the azimuthal angle goes from 0 to 2 pi, what you have is the surface of a cone. So this is the surface of a cone whose half angle is theta. The half angle at the base is theta, and that surface, which goes all the way to infinity, is what theta equal to constant is. When theta equal to 0, this cone gets degenerated into the positive z axis. When theta is pi, the cone degenerates into the negative z axis. And what happens when theta is equal to pi over 2? This cone angle opens out till it becomes the xy plane itself. So in the special case theta equal to pi over 2, the surface theta equal to constant corresponds to the xy plane itself. So it's a very simple geometrical interpretation. Now what about the unit vectors, and what about the line element? Well, those are interesting quantities to look at. Let's do that. So here's x, here's y, here's z again, and we have an arbitrary point r. This is r vector, and therefore the unit vector in the radial direction is just E sub r, just extends E sub r. It is in the direction of increasing distance from the origin without changing theta and phi. Now this angle was theta. Therefore, in the direction of increasing theta, you have this vector here, which is E theta at this point. It is quite clear that E theta is also dependent on the coordinates. And what about E phi? Well, if I draw my original projection as before, so I draw my projection here in this fashion, and this angle is phi, and therefore an increase in phi will take me into the plane of the board, which is equivalent to going in there, inside E phi. That is the unit vector. This is supposed to be parallel to that. So now you can see that if I take ER and take a cross product with E theta, I am moving into E phi. So I have the first of these relations, ER cross E theta equal to E phi. Then E theta cross E phi. So I go from E theta, go into the plane of the board, twist this around, and I move along the radial direction. So this is E sub r. And finally E phi cross ER. So I start with phi and move up a screwdriver, turn this vector into that vector here, and the screwdriver moves in the direction of E theta, this, like so. So once again we have a right-handed triad of vectors, and we have these relations, cross product relations between them. Of course, the dot product of every vector with itself gives you unity, because they are unit vectors here. What about the line element itself now? And what about R vector itself? Well, we know by definition, we know that R equal to R times ER. Nothing else, that is it. But this is position dependent. This thing here, the unit vector, is position dependent. So its derivatives are going to be fairly complicated. On the other hand, we could ask what's the magnitude of a line element. So I have 2 points, one here and one here. This has got some distance from the origin, that's got a different distance, different r, different theta, and different phi, and so on. What does one do now to find out what the line element is? Well, keep the others constant and vary one coordinate at a time, and then use the Pythagoras theorem. Okay. So if you keep theta and r constant and shift only phi, then what you are doing is to shifting by this vector is shifted to that in this direction, inwards. So if this angle is d phi and this distance is rho, then it's rho times d phi that you have shifted the line element by. But remember, as before, we need to write down the relations between Cartesian coordinates and spherical polar coordinates. So let me do that in a minute. Z is equal to r times cos theta. That's very clear from this figure itself. Let's do the figure again. There's my point r, vector r. This is the distance r here. That's the projection out here. This is phi, and this is theta. Okay. Now, from the way this figure is constructed, this is the vertical coordinate. This is the vertical coordinate of this point, above distance above the xy plane. And what is this point? Well, if this is r and this angle is theta, then the base is r cos theta, and that's what z is. So that's the first relation out here. On the other hand, this distance, the vertical, is r times sine theta. So this is r sine theta, and this is r sine theta. But that's what we call rho, the distance in the xy plane to this point of projection. So x was equal to rho cos phi. We already know that from plane polar coordinates. But rho cos phi is the same as r sine theta cos phi. And similarly, y was equal to rho sine phi, that's equal to r sine theta sine phi. So these are the relations which relate the spherical polar coordinates r theta phi to the Cartesian coordinates of a point x, y, z. So it's immediately clear that x squared plus y squared plus z squared, first of all the sine squared theta phi plus cos squared phi gives you 1, and then the sine squared theta plus cos squared theta gives you 1. So x squared plus y squared plus z squared is r squared, which is what you want. Okay. And what are the inverse relations for this? The inverse relations are equally straightforward. It's immediately clear that theta is equal to cos inverse, if you like, doesn't matter how you write this, it's equal to z divided by r, so this is equal to cos inverse. You can write it in this fashion. Okay. You could also write this in terms of tan inverse, so you could also write this as tan inverse. Well, from this relation you can see that the tangent of theta is this vertical divided by this horizontal, so it's rho divided by z in this here, which is equal to r sine theta divided over by this quantity, by this base here. So you can write this in a number of ways, it doesn't matter, you do so, I leave it to you to do that. Phi on the other hand, as before, is tan inverse y over x, and of course r equal to square root of z squared. Okay. And the ranges we have already written down. It is important for you to remember that the polar angle theta runs from 0 to pi, including the value 0 and including the value pi. On the other hand, phi runs from 0 to 2 pi, 0 less than equal to phi less than 2 pi to make it single valued here. As before, in the case of plane polar coordinates, we discovered that the origin itself has no definite azimuthal angle. There is no unique angle associated with the origin itself, where rho is 0. In exactly the same way, here the whole z axis, this line, has an indeterminate value of phi. Because there is no question of saying there is a specific phi associated with this line. There are these mapping singularities when you go from Cartesian coordinates to any other coordinate system, but we know what they are and they are quite harmless, but one has to take them into account. Okay. So I was starting to say what the line element is in this case, and the way to discover the line element is to use the Pythagoras theorem exactly as we did for Cartesian coordinates. So if you keep r constant and theta constant and change phi alone, you move in, you increase phi, then the distance you move by is this arc rho and then an arc d phi. So it's immediately clear that the contribution which you get from that portion is rho d phi the whole squared, but rho is equal to r sine theta. So there is going to be a term here which comes plus rho squared r squared sine squared theta d phi whole squared. That is the hardest term actually. The next thing is, let us keep phi constant, let us keep r constant and change theta alone, and this is theta. So when you increase theta you go there, this arc, this radius is r and the angle is d theta. So the arc is r d theta, and therefore you have r squared d theta whole squared plus, and now the simplest of them all, which is you keep phi constant, you keep theta constant and just change r in the same direction, you move a distance dr, and that's it. We have already seen we have a triad ER, E theta and E phi, and together with this expression for the line element, this tells you all that you need to do about spherical polar coordinates. It is an interesting question to ask, what is the functional dependence of ER on the position r theta phi. Similarly, E theta on r theta phi, E phi on r theta phi. Well, it's easy to guess some of these dependencies fairly straightforwardly. First of all, if you have a point here and I increase this, that's E sub r, and I go further down and increase it, it's still in the same direction, nothing has changed. So there's really no r dependence at all in any of these quantities. So right away you see that ER cannot depend on r. I'm going to leave it to you as an exercise to figure out, and we will write the answer down at some stage, to figure out what is the theta and phi dependence of this unit vector, and similarly for the other two unit vectors. This is an interesting exercise, and it also will help you to picture what's going on with these coordinates carefully. The important thing, crucial point, is the position dependence of these unit vectors. That's very important, because when you go to some other point, these unit vectors will look this fashion. So this coordinate axis will get tilted, and one has to take that into account, unlike Cartesian coordinates where the unit vectors don't change at all. On the other hand, when would you use spherical polar coordinates? Just as I would use it in cases of cylindrical coordinates, useful in cases of axial symmetry, spherical polar coordinates would be useful in cases of spherical symmetry, of course. Where you have something which does not depend on the actual polar angle or the azimuthal angle, but only on the radial distance from the origin, such as the inverse square law of force. This force depends only on the distance from the origin, in magnitude at least. It does not depend on which direction you are in with respect to the center of attraction or repulsion, and then it's very useful in such cases to use spherical polar coordinates. We will do so very often whenever we deal with a problem with spherical symmetry. The most important case of all in mechanics would be where there's a force of attraction or repulsion from some center of force, and it's very conveniently chosen to be the origin, and the problem is most conveniently solved by looking at spherical polar coordinates. But for that, one needs to know how to use the unit vectors in spherical polar coordinates, how to write down the line element and so on, which is why I have taken this mathematical digression through this other coordinate systems, but we will revert to physics very shortly.